Good afternoon, ladies and gentlemen, and welcome to the MetaMaterial MetaMat series of webinars. Today, it's my pleasure to have Marc Dubois from Mutliwave Imaging from Marseille in France. And Marc is going to present his work on MRI metamaterials.
Okay, thank you, Mama. So, well, I'll present my work, but certainly the work of many people. As you can see, by French tradition, there's like lots of logo always on the front page. But so let's start. So my name is Marc Dubois. I'm the director here in Mutliwave Imaging, which is a French startup company based in Marseille, right next door to Institut Fresnel, with whom you will hear a lot today, because basically this work was done while I was a postdoc for the MCube project. So MCube project was a European funded project that lasted from, I think, 2017 to 2021, and it ended just last year. And the main topic was to promote MRI applications for electromagnetic metamaterials. And due to the specification of MRI application, it was mostly focused in the, let's say, radiofrequency part of the spectrum, which is what you need to do to use for MRI. So I will later in the talk, I hope everybody will understand more precisely the title here, but what we're gonna do is to see, I will first acknowledge all my colleagues here. So as I said, this work has a lot to do with Institut Fresnel, especially Reda Abdedaim and Stéphane Enoch, that were actually leading this project. The team also here in Mutliwave Imaging, the CRMBM, which is the Center of Research for Magnetic Resonance in Biology and Medicine in Marseille. CEA Neurospin, which is also a division of French CEA activities related to MRI, specifically for brain. And the Institut Langevin that was also part of this project. So all of this here is, most of the team was based in Marseille during this time. So to start, I will start with a little background and motivation, because I understand this was mainly focused on acoustic and mechanical, so don't be afraid. I will try to just explain what I need in terms of MRI, how it works, such that you will understand the benefits of the solution we propose. Mostly then I will show you what people have been doing in metamaterials and meta-atoms in the realm of metamaterial for MRI. Then I will try to focus a bit more on these two works that we've been doing that are kind of connected, which is first topic that was to look into this KERKER effect. I guess some of you may know which is a specific scattering condition with hybridized metamaterial that we used for MRI purpose. And also we had worked then on how to reduce the size of our meta-atoms such that they fit nicely and they are easy to use for the clinician in the end. So to start with the basic of the MRI acquisition, that's why I put MRI acquisition in a nutshell here. So the main goal, what you need in fact to do an MRI scan are mostly these big static magnet that can produce a highly homogeneous magnetic field that is permanent. In fact, you may know that it's never turned off. Like even if there's no one in the scanner, the magnet is always on because it just takes a week to turn on. So you don't want to turn it off when you finish your day. So be careful when you go around MRI because the magnet's always on. And we call it this one B naught, and by convention, it's around the Z-axis. And what happens, in fact, when you put like a body inside the MRI, which is mainly composed of water, so luckily humans feel this purpose, there is a net magnetization that is produced. So it's usually due to the fact that the water molecules tend to align a bit more towards in the same direction as the magnetic field. But you will see most of the time people talk like all the magnets align. And this picture is a bit wrong, like because in fact, due to the temperature and the agitation of the spins, there's probably only 1 in a million that gets actually aligned with the B naught. But it's enough actually to do an image, which is really nice. And so so you create this net magnetization, which is this green vector along Z. that is composed, in fact, of many atoms that are spinning. It's like the resultant of all the magnetic interaction. And it is spinning precisely at a frequency that we call the Larmor frequency that depends on the nuclei you are looking into. So when we do MRI on human, most of the time we will use the hydrogen because there are 2 hydrogen atoms per water molecule, and that's the one that is the most present in the body. And if you do gamma for the hydrogen, this is roughly 40 megahertz per Tesla. So if you go to hospital, you have today 1.5 and 3 Tesla MRI machines that work at 65 and 130 megahertz roughly. And today's work will be dedicated to stronger magnets, which is kind of like the cutting edge technology for the last 5-6 years for MRI, which is 7 Tesla magnet, much stronger. And just to give you a perspective, today the biggest magnet is ramping up. I think it's ready now. The first images were out in Saclay in Eurospin with 11.7 Tesla, which is the highest magnetic field right now for whole body for human. And so then you have this magnet this magnetization that is spinning at the Larmor frequency. And to be able to map it, you will need a radio frequency coil that you will place, for example, like here, close to the part of the body that you want to image. And when you do so, this RF coil needs to produce a radio frequency magnetic field at the Larmor frequency that is perpendicular to B0, called B1. So we hear a lot of B1 today. And there is 2 phases that are done with this radio frequency coil. One is the transmit. The transmit field is used to tip the magnetization in the transverse plane such that you are able to detect it. And once the transmit phase, let's say, is over, once you're done exciting the spins and you're sure you have the angle, the flip angle that you want, you just let the system relax and you pick up the signal that you obtain, which we call the free induction decay. And by analyzing the different frequencies in this signal, you are able to reproduce the image. So you do kind of like a 2D Fourier transform of these FIDs all together, and you get the image of the signal. So that's roughly how MRI works. And like I said, why do people want to go with these stronger and stronger magnets? And the main goal is for SNR. So today, if you go to medical imaging, if you discuss with people, let's say not gold standard, but the easiest one, yet a bit dangerous, is the CT scan that is meant with this rotating X-ray scanner that can produce really precise image in the blink of an eye. And so a lot of people like this one because it's very fast. Yet it is X-ray, so you can't be exposed all day with this one. So for, let's say, long studies where you want to scan the same patient over and over, if you want to detect small changes and stuff, X-ray is actually quite hard because you have to repeat scans and scan over and over. So people like MRI, especially for neurology, but for many different biological or medical application, because you can scan the same. The risk associated with MRI is much less than other modalities such as X-ray. And so, yet the problem is that MRI takes much longer. We are talking for a decent image like a few minutes instead of a few seconds. And why? It's simply because, like I said, there's only 1 atom per million that is aligned with the B0. And if you make the B0 stronger, there's more and more of these atoms or nuclei that are aligned with B0. And with that, you can image faster because you need less averaging, let's say, of the signal. And so that's especially why people have been increasing this B0, this 1.5, 3, 7 Tesla, all the way up for specific, really tiny magnets. So they are like maybe just a few centimeters across that can go up to 25 or close to 30 Tesla, I think now, with Larmor frequency up to the gigahertz. Now there's a problem. In the very early days of the MRI, in order to make a nice image, we said that we need to apply this B1 RF radio frequency field to the body. And it was convenient because you would need to have this B1 to be the same in amplitude and phase everywhere across the body. And what I want to show here is that as you increase the B0 to gain your SNR, to make your image faster or the image even more precise, well, what you lose is that the wavelengths of the radio frequency field inside the body, which at the beginning with 64 megahertz is huge. We are talking something like 5 meters. So you're fine. Like the amplitude and phase in the body will be exactly the same everywhere. But as you increase and increase, you will see, for example, in 7 Tesla. So if you look at the wavelengths inside water, because epsilon is around 80, so that's an index of refraction of 9 if we talk about optics. You will get, for example, the 7 Tesla wavelengths that's represented here in this gray box to be roughly the size of like 10 centimeter. And sadly, 10 centimeter is roughly, usually the diameter of the head here is around 16, 18 centimeter. And so with that comes a big problem, is that you see appearing a sort of interference. So it's not like a perfect interference because actually the salt in the blood and in the tissues attenuate the radio frequency quite a lot. So you get like sort of a damp oscillation, but still you see this oscillation you see here. When you have a Larmor frequency of 300 megahertz in 7 Tesla, the wavelength in the body is around 11 to 12 centimeter. And that's what you see here. You see this oscillation where you have two areas where the field kind of like interfere destructively. So you have a dark area because you don't tip the magnetization enough. And in the center, you have a brighter spot because you tip more than what you were aiming for. And so that's our main goal. It's like we would like to have the benefits of the 7 Tesla in terms of SNR, but with the homogeneity that was achieved before. And typically, the RF coil, so this is just like an image of what approximatively look an RF coil when you use head imaging for, at least for transmission. You have the head. There's always a part that is actively connected to the scanner where you deliver the power and it creates the transverse magnetic field. So this one is specific. It's called the birdcage coil, just simply by the look it has. And there is usually around a shield plate just to shield the environment of the coil such that if you change something in the environment, it won't affect the properties of the coil. That's typically how it looks. And so what people did, so this coil is specific because you only excite the coil in 1 or 2 points to have the B1 field created in the brain. And what people did is like, okay, now I have a pattern of interference that I need to control. What if I have, instead of having one channel, let's say to control my system, I have plenty of those. And that was basically the creation of, or the start of what people call parallel transmission, where simply the idea is instead of having just one coil that encompasses all the body, you have many of these. And you can control, let's say, amplitude and phase, for example. And if you do so, you are able to find the correct amplitude and phase of the RF pulse you sent in each element, and you can get much nicer image. So this is here, for example, an example where you start to have here kind of darker area, as exactly the same as the image before. And once you find this good shimming condition, then you can recover the contrast, which is the most important, because this image on the left, some clinician will say, due to this RF artifact, I'm not able to do a diagnosis because I don't know what's hidden in this dark area. So once you recover the contrast in these places, then the clinician can use it. So now this comes with a caveat. It's that I said before that the MRI is safe, much safer than X-ray, and transmit does not follows this trend. But we have to check what we call the specific absorption rate, which is exactly the amount of power. So when we send the RF pulse, we know that there is a part that gets into a magnetic field and there's a part that goes into electric field. And this electric field gets absorbed by human tissue. And exactly, if you see, right, as of today, more and more in the commercial TV spots for cell phones, for example, you will see in the bottom specific absorption rate, that much watt per kilogram. And so that's the amount of radiation your body absorbs when you use your phone. And so we have to follow in MRI exactly the same trend, because this is roughly microwave, radio frequency. We are on the same part of the spectrum, so the same regulation applies basically. And you need so to make sure that your SAR, specific absorption rate, is within limits. And that is actually much, much harder to do when you play around with this amplitude and phase all the time. Especially, imagine you have an algorithm that you want to make it search for what's the best configuration, but okay, you know where it ends, but you don't know where by which point it passes before it gets there, and maybe some are dangerous. And so this is why this parallel transmission is a lot used in research, but still not available, at least not at its full potential in the clinical world, in let's say commercial world, but in the hospitals. And so what people thought is like, okay, if we can't add this new channel, let's try to modify the pattern of the field by inserting scatterers, basically, inside the RF coil. And the first one, the first work started to begin around the concept of high permittivity pads. So because the head is something like epsilon equals 80, people thought, okay, let's put some pads, so really just tiny pads, approximately 10 or 20 centimeters square, filled with perovskite powder that gives you epsilon around 120, 150, and you place it inside close to the patient. And for example, here you see an example. So the reference is classically the B1 map. You see the bright spot at the center and the spot where there is a very low field. And once I put an MRI pad filled with this material by AMPLITUDE, then I can see I have a huge increase of the B1 field. And that's just one example to show you how you can control the RF field emission due to the electric material. So now, again, this dielectric material, they come with some issues, something you need to pay attention. Some materials, by AMPLITUDE is part of it, can be dangerous. It's not like completely, it's not killing you if you see it, but it's irritative. You know, there's all the list of chemical risk associated with it. And it does not age well. So usually you have to make a mixture of powder and water to find the right epsilon to make it work nicely. This is designed usually with simulation, but you need to mix. And the problem is with the time and the usage of this pad, they tend to demix, where the water gets in one part, the powder somewhere else, and then they don't work anymore. And there is other problems for storage and stuff. And so the idea that Reda Stefan came with was to, okay, let's find metamaterial that can fit this purpose. Like we know metamaterial, they are a lot of time used to reproduce specific epsilon nu or density and bulk modulus for acoustics. So let's try to see what we can do in the metamaterial to be able to have similar effect as the pad and have something that is just made of metal and that will last forever and be very, very cost effective. And so this is, yeah, in more details how the electric pads work, but I don't think I will jump into that. But here, for example, is one example. That's the example of the optimization of how you want to, what's the epsilon that you need to find for the pad. So usually what we do when we start, and we do the same for metamaterials, so that's a good part of the lecture. We use a lot the FEM or FDTD to calculate for the full Maxwell's equation to get what is the magnetic field distribution inside the head. And so we have a bunch of phantoms that are exactly the same size of the head and filled with liquid that has properties close to the properties of the tissues. And here, for example, you put this square of the electric pads and you increase the permittivity and you look at what is the field distribution. And like I said, around this 120, 150, you find like moments where the magnetic field gets more homogeneous than what you started with. So you're very happy with this. But what's surprising is that usually more epsilon means more efficiency, but actually maybe the pads get more efficient, but the field gets kind of scrambled around. And this is also one thing we wanted to do with the metamaterials, is to try to avoid to be in this situation here and to find the optimal points. So that's conclude the small introduction, which is okay. What do we want? We want a simple and reconfigurable device to manage the radio frequency field inside the MRI coil. And to do that, the metamaterials, at least electromagnetic metamaterials, they are here because they have these properties, and if you design them well, with a periodic arrangement of resonant occlusion, you can reach many different properties, such as negative index, hyperbolic material by anisotropy, and more recently, I guess, a lot of work on topological metamaterial. So the issue is with the radio frequency, and we are talking wavelengths that are kind of like around 1 meter at 300 megahertz outside of the body. So if we want to have something really like a 3D or 2D metamaterial, that's going to take a lot of room inside our MRI scanner, and we won't be able to fit it close to the patient. So what we looked around mostly is to what we call this meta-atom, that in the sense is like how it's taking the metamaterial approach the other way. It's like this one, the top one, the 3D metamaterial, the bulk metamaterial, usually you do this block equation and you solve for dispersion bands and you're looking parts where you have high index or low index. Meta-atom is more, I have a bunch of resonators, usually it's a small number, and I just try to look at how the eigennodes of each other interact and give emerging properties. And I think this was developed quite early in this paper from Naomi Alas and Nordlander, where they show like how the properties of a nanoshell kind of emerge from the resonance of the sphere, the resonance of the cavity, and when you merge them together in this nanoshell, you have interactions of these eigennodes and some splitting, and they have different properties, and that's what we were looking into. Of course, there was previous work. I mean, I guess a lot of people from Imperial College are here, but in the early 2000s, in the group of John Pendry, I think he was collaborating, couldn't remember exactly the team, but there was some work on B0 cloaking and on radiofrequency metamaterials, also in Spain, where they built this kind of MRI lenses. With more of this 3D bulk metamaterial approach, and also work from Université Catholique de Louvain, a collaborator of us for the MQ project, that used the wire medium that was developed by Pavel Belov to guide the electromagnetic waves inside scanners, for example. So there is already a tradition of metamaterial applied for MRI, but this was more looking into the bulk metamaterial ideas, I would say. And more recently, there was some work mostly from the ITMO team, that is, the logo is not, yeah, ITMO University, it's also a collaborator of us, where they explore also ideas of metasurface, and also extremely thin artificial dielectric made of like capacitive patches that are face on, face back on substrate like this to control radio frequency fields. Just to give them thumbs up because it's really nice work. And so here's in a nutshell also our hybridized meta-atom. So what I represent here is a calculation where if you use impedance matrix approach that was developed mostly in the antenna theory. If you read some books like the Balanis theory of antennas, you will find like ways of calculating how metal parts, like just straight dipoles or loops, interact with each other, and especially how the impedance changes when they are near a source and if their distance is relatively close short compared to the wavelengths. And what you will see, and that's really well explained in this early work from Reda and the Langevin team, it's you would expect to see again this hybridization principle where at the beginning you have the self-resonance of a straight dipole that's kind of straightforward, just like the current flowing, kind of like a sine wave on the electric dipole with two nuts at the end because of the open circuit. And then when I approach another very close, then I can find two different modes that I know where the current is flowing in phase or out of phase, and so on and so forth. So the more metallic parts I will add, the more hybridized resonance I will get. And what's really interesting, especially with this arrangement of 4 wires, is that you will find very different behavior for the electromagnetic waves, depending on the first one, for example, which we call the electric polarizability, because it's basically will look pretty much the same as this one, just with somehow a different quality factor. And this one that create, in fact, that have the capability to store magnetic field inside, because they recreate a sort of a loop that will be able to have a magnetic field inside, where this one, if you take Biot-SAVAR, you won't see magnetic field inside. So they start to have very different properties. And what we do is that if you put these 4 wires and you put an electric dipole that will try to radiate energy, and you look, okay, what is the power radiated by this birdcage leg, or just this emitter, in the presence of this element. And this is how the radiated power will look like. So you have in the dotted black line is the single wire, the wire alone. And as expected, there's kind of a single resonance, and close to when the wavelength is, the half wavelength resonance is met, so very close to 0.5 meter, you will get sort of resonant effect. And now, if I have 4 wires, I have my HMI and the 4 wires very close to each other, I would see 2 effects, mostly that we represent here. So there's 2 areas that we are interested in. We have the yellow area, which basically correspond to this electric polarizability. So that's the contribution of this mode that is basically a broader version of the dotted one. And that's actually quite useful, because in MRI, what you would see is that most of the time we don't want to work exactly at the resonant frequency, because as we will put this thing close to a person head, and because person to person, we don't have the same size, the composition roughly the same, but mostly the size, you will see shifts. I mean, due to the environment change, you will see effects on the dipole. And you don't want that, because it means efficiency won't be the same across persons. So most likely we will work in this part of the spectrum here. But again, with a single wire, that's rather steep. And so to be able to have this to work for the most people, you want this curve to be a bit high to see some effect, but also with the slope like a bit smoother. And that's what we are able to achieve in this yellow area with this larger version of the electric dipole mode. You have it here. And on the other end, you see this very sharp contribution that is coming, in fact, from these 2 modes here that are degenerated here. But because they are able to store the magnetic energy, they can resonate for a very long time, like a bell. And so you will see this very sharp contribution. And interestingly, with the interference of this magnetic and electric polarizability, you create the realm where you can observe this kind of KERKER effect, which is in fact the result of exciting 2 modes with opposite symmetries properties, which is able to completely backscatter the signal, or to and basically to give you extremely directive far-field antenna. So this was a lot used for far-field control of emission of light or microwaves. But we will see here that we can explore this also in MRI, which is really nice. And like I said, yeah, we have this electric dipole behavior that where the lower quality factor gives you a much more resilient element to play with. So we will explore then in MRI these two different aspects. So just to conclude this part, like we found this good candidate, these 4 wires HMA, with a good predictable behavior, because right now this calculation was just pure theoretical calculation with some integrals to have numerically, but it's not pure analytical, but it's just theoretical calculation. And so let's see how it looks a bit further. So now with the same approach of impedance matrix, what you can do is we can recreate the environment of the MRI. So to do first, we will create the birdcage. So the birdcage is just this collection of straight dipole that we can place with a radius that's here 13 centimeter, and that we can feed each and every one of them with the current that we know is going to be set in the experimental condition. And you see, for example, in this image that if you put the right phase and amplitude of current, you create this very homogeneous magnetic field. So here it's very homogeneous because there's no one inside. So the wavelength is 1 meter, so there's no effect. And what we put our 4 metallic rods that form the hybridized meta-atom, and we will vary the length of these 4 rods. And we'll vary the length from here 35 centimeter to 60 centimeter. And again, you have the response in blue. This is the B1 enhancement. So this is in this red area. What's the difference between with the HMA and without the HMA? Just the ratio. And if you use a single wire, you see you have a moderate gain, and then you start to fade away when the resonance passes. And if you do the same with the HMA, this is what you find. You find first this red, the big bump that we were expected that starts earlier, and that's a bit smoother than the blue one. And then you see 2 interesting conditions, which are these close to this KERKER scattering condition. The first one, which is labeled here, number second, is represented here. So basically what you see here is that, in fact, this HMA, when it is very close to 0.5, so I think here it's 49 centimeter in that case, you have most of the energy that gets reflected back to the actual feed. And in fact, very low energy is projected inside the patient. So you see this decay of the B1 plus in the region nearby. So actually, we don't want that. And then right next to it, because you just have basically what you see between 2 and 3 is just the fact that when you go across this magnetic mode that is very high in quality factor, you see the phase change between before and after the resonant frequency. So before you are sort of out of phase, and so you have destructive interference between the electric and magnetic mode. And once you pass this point, then you flip the phase of the magnetic mode, and suddenly you have big boosts of energy towards the patient, and that's really exciting. So we wanted to work with this also. And so we wanted to test this. So here's in experiment how it looks. So you will see a big ball of oil. So we use oil here because we wanted really to reproduce the same image as you saw in the slide before. And the good thing is oil, at least in electromagnetics and in radio frequency, is almost transparent. It's like epsilon equals 4, so we won't see any effect of any wavelength effects, and we know we can just use it to map actually the electric field without disturbing the HMA or the coil. And this is the sequence we've been using to acquire B1 imaging directly with the scanner. And so we acquire these images one by one, and since we have this telescopic wire, we can pull on them to go again from this 40 centimeter to 60 centimeter, and every time acquire the image of the magnetic field. And that's exactly what we found here. We were able to find, again, by changing the wire length ever so slightly, to find these two regions where we have first, when we approach this 49, like a decay of the magnetic field nearby, always plotting the field close to the HMA, and then this big enhancement. And just to give you a perspective, this is the actual experimental data that we acquired, and below is the data that we just saw before. So we have an excellent agreement pretty much at the same frequency here. So we are very happy with this, because to be noted, this is also the first demonstration, at least, of this near-field KERKER effect at the radio frequency field. So some may argue that Yagi-Uda antenna is a similar concept, but at least demonstrated in this idea of KERKER effect, it was like we didn't find such a result in the literature. And so, like I said, so this is interesting, but you see the fact that you switch in just 1 centimeter, you switch from something disastrous to something too strong, is not very nice actually to be used on a daily basis. So this was mostly this area, and now we want to talk, like the rest of the talk, we'll focus more on the MRI application, how it's beneficial for the persons, and so we will use this part here. So most of the time the wires will be 42, 44 centimeters, and we will focus on that part. And this is how it looks now. When you put, so we use the phantom, which is exactly shaped as a human head. So it's called SAM for specific anthropomorphic mannequin, and that's the one that a lot of telecom companies actually use. And you place it again in a similar bird cage, and we have the 4 wires that are 42 centimeters, and they can be placed, in fact, between the person and the coil. And what you see when you do so is you have, again, if you remember this reference image, where we see always these two shadows that are on the side of the head due to the wavelength effect, because this time we have epsilon that is roughly 60 or 70 here in the phantom. So we start to see this wavelength effect. And this is how the signal looks when you put like a 42 centimeter HMA nearby. And so when you make a cut along this line, you see really the beneficial effects, like the signal stay the same everywhere. It's much stronger here, but just the fact that you are able to make this leap is the contrast recovery that the doctors need to make an appreciation and to make a diagnosis in persons. And so this is because we wanted to also, that's more for the MRI specialists, but as we say, the RF coil is used at the same time for transmit and receive. And what we were able to show here is like in the case where we do have in the blue, this blue ball represent the sort of helmet that will be in the coil, and that will in fact has elements, very small elements, being able to capture the signal better than the big breakage. And what you see here is before and after introduction of HMA. So the blue and yellow here, this part is the relative flip angle of the B1 maps. So we have an effect on the transmit, RF transmit coil, which we were striving for, and so it is still working. You see the improvement in this dark blue here gets like filled with signal here, but also some benefits as well for the SNR, which is mostly coming from the receiver array. So that's something we wanted to be sure of, because that's typically the paradigm that is used every day in hospital, where you have a separate transmit and receive coil. So it's extremely interesting that this technology is compatible with the paradigm that is used in clinical settings. And now, so all the work we've been doing so far, like of course we tried here and then, but was focused on, okay, let's make one element that is working very nicely. And of course we did try, because you see every time this problem of homogeneity is bilateral, so you have issues on both sides of the brain. And what happens when you put two of these, one on each side of the brain, is a bit sad for us, because it didn't work the first time, but we are working on it. Is that you don't see such a big effect. So just to remind you, when you put one on the side, you have a very large enhancement here on the side. But once you put two, you see you have some homogeneity gain, but you need to inject more power in the birdcage. We're not exactly sure why. And so one thing we saw is that because these two scatterers, they are very close and they can talk to each other. So we were thinking like the energy from one can couple to the other, and this may also detune the birdcage coil, meaning that the efficiency of the antenna, once you put too many scatterers inside, gets reduced. And so one thing we were exploring is, let's shrink the size of this dipole element such that you can make a nice image. So that's what I conclude here with this hybridized metamaterial and KERKER effects. Like, we have a good candidate for a single side, and we have side where we compare with dielectric pads, and they really are look alike. However, if we want to homogenize the field everywhere, the length is too long, and so the effect, the shimming effect is too strong. And this is why we then turn into means of keeping these electric dipole properties, but on a smaller pattern, on a smaller footprint. And again, we looked a bit into literature on this fractal inspired design, and there is some example already used to make MRI codes with this work from the group in so yeah. Some group also here in England that use the KERKER to create loops, and also group from, I think it was from Singapore, where they exploit this Hilbert metamaterial, Hilbert fractal, to have single element coil. And the main idea, as I said, was to reduce the footprint of this straight electric dipole. So we did a modification. So we started with to look into the response of such elements, and we found that if we replicate them and connect them in series, we create this structure here. And it is able actually to resonate and to radiate field very similarly to a straight electric dipole, although having the length reduced here to 10 centimeter, where if you remember, the previous structure was 40 centimeter long. And so just to convince you, this is looking at the magnetic field that is produced along this red line. If I input the power here in this red cone, and you see here, in fact, this one look like a split ring resonator. So you create the magnetic field kind of a bit tilted, and that's why if I'm at the center of the red line, roughly 6 centimeter away, I have equal contribution of X and Y components, because the field is kind of going downwards. Whereas when you do the same measurement with this device that was a bit modified, so it's not strictly a fractal, so that's why we have fractal-inspired dipoles. You see that mostly all the magnetic field is due to the HY, which is parallel to the plane containing the structure, which is exactly what you would have if you do this calculation with a straight electric dipole. So we were really happy with these results. And this is to show the benefits. So I compared the magnetic field inside the birdcage with this simulation result, the magnetic field in the birdcage. So basically the B1 is just the combination of these because we use the circular polarized field. But what you see is if you take really the true Hilbert transform, so there is effect on both H, X, and Y, and you have a, let's say, minor effect on B1 plus. Whereas if you're able to use this fractal-inspired dipole that we built, we have a much stronger effect on the HY component, and you create like a better B1 plus distribution, especially here in this part. And so we produce these, and to also to move a bit away from the 3D structure, we have this one now that are printed directly on FR4 substrate. So this green substrate is the substrate that you will have for most of the electronic cards that you can get in regular daily products, except that I think this one is really thin, maybe down to 0.4 millimeters, so it starts to get a bit flexible, and you can place them. You can actually tape them inside the MRI coil next to the head of Sam, and we placed one on each side. And what you can see here again, these are B1 experimental map that were acquired. The first line is the reference, and you will always recognize this kind of pattern where you have low regions with low magnetic field and bright spot at the center. So this is if you cut somewhere there, for example, different projection coordinate axial. And what you can do with and without is you make the ratio of this magnetic map. And what we're really happy with is that now in this image, you start to see improvements really on each side without having destruction of the magnetic field somewhere else. So that's very good news because it means that this device, you are able to increase the field in region of interest without perturbing the other structure that you would normally see in the brain. And so this is really highly beneficial to the clinicians. And you see some enhancements, so to give some numbers, in really close to the fractal, we have strong enhancement by the order of like 60–50%. And when you average it, we go to like 20% increase. That is what you will have for like a moderate epsilon pad. And this is how the image look like, let's say, if you were to do regular MRI acquisition on SAM, and you see really the enhancement of B1 plus and also a bit of SNR. And this was mostly the work of Tania Vergara, which defended the thesis a few months ago and is now also working with us at Mutliwave. So yeah, so that's the conclusion of this part. So there is a fundamental trade-off, as we saw by looking at this Q factor. Like you want to have Q factor that is low enough such that you are able to be resilient to any change in the coil, not in the coil, but in the environment of the coil. Then there is this effect of efficiency. We saw that the longer the structure, the more likely you are to radiate field. The problem is, for example, in the case of the HMA, this was too strong and possibly perturbed the original coil that was present. And you want also to be careful with how the subject loads the system. Let's say you don't want the subject to completely damp the effects. So to conclude, this metamaterial concept applied to MRI can lead to really compact, thin, flexible, and long-lasting device that have this ability to control the RF magnetic field and to be used in clinical settings, let's say, in favor of this parallel transmit application. We've seen that the simultaneous excitation of electric and magnetic response can give us interesting physical effects. And the fact that it can be addressed independently is actually useful because not all the RF coil are birdcage coil. And so you want to be able to change this behavior depending on what coil you want to start with. We will see the direction we are going right now is to also see how we can use similar technology but at lower magnetic field. So all the first points were for 7 Tesla MRI, but there is already, I think today, kind of almost 100, probably 7 Tesla scanner in the world, whereas there's probably 10,000 3 Tesla scanners. And they have also in some imaging for the back or for the abdominal imaging, there is also some similar inhomogeneities due to B1 effect. So we are looking into this. And clearly future challenges, there are what I just named before. So you want to have something that can be easily installed on volunteers, that has good performance, and that is robust. That means the same response when you change from person to person, and that can help in this inhomogeneities improvement, because that's the only thing that can render the images and the diagnosis useful. And to give some perspective, the MQ project has finished almost a year ago. Part of the consortium is now gathered into the M1 project. That's kind of like in the European framework, the next one in terms of TRL, where we took this technique of HMA and we tried to look, okay, how can we still balance this idea of bandwidth and efficiency to obtain efficient coil? And you see here like some images where we were able to take the HMA and make it work on this bilateral situation that we were not able to do before, or at least with the FRACTAL, but here with a different design. So this was interesting. And we also, with the company, we collaborate heavily with Institut Fresnel and CRMBN, and we are participating into this AMIDEX-funded medical share of medical imaging, where we are developing new ideas such as these metamaterial pads, the flexible coils, and also we are looking into having wireless system and wireless coils, because we identify this to be quite taking some time to install on people, quite heavy, could be stressful for the patient, and so we want to have a system that is more easy to be used. And with this, I think I will conclude here, and I'll be happy to take questions if there's any.
Thank you very much, Marc, for this very nice talk. So we have time for questions. So just please come on, or if you don't have a microphone, you can ask the questions in the chat, and I will read them.